Water is essential to every living organism on Earth. It supports ecosystems, drives economic activities, and provides one of our most valuable natural resources. However, increasing human activities have placed immense pressure on water quality, making pollution one of today's most urgent environmental concerns. When we think of water pollution, we usually picture the obvious, floating plastic or oil slicks, but the most critical threats to our global water systems are often forces that we cannot physically see, creating a major problem for environmental scientists who cannot manage, regulate, or clean up a contaminant if they don't know where it is or where it originated. These invisible threats generally fall into three specific categories: biological organisms, industrial chemical compounds, and physical temperature shifts. Solving modern water pollution requires moving beyond simply looking at the surface of a river, to actively finding ways to make those hidden threats visible. The traditional method for testing water quality involves a scientist standing at the edge of a river, taking a physical sample, and bringing it back to a lab for analysis.
But finding the source of pollution requires a different perspective. Instead of relying solely on individual water samples, scientists look from above. Using geographic information systems and remote sensing, they monitor entire watersheds, revealing pollution pathways that would otherwise remain invisible. This shift from local observation to landscape-scale analysis allows environmental scientists to trace contamination back to its origin. Although modern technologies have significantly improved environmental monitoring, tracking water pollution remains one of the greatest challenges in environmental science. Unlike solid waste or air pollution, contaminants in water are constantly moving and changing, making them far more difficult to observe and control. Once pollutants enter a river, lake, or coastal water, they rarely remain in one location. Instead, they are transported by river currents, rainfall, tides, and seasonal weather patterns. As they move, contaminants spread, dilute, and mix with surrounding water, often traveling far beyond their original source. The movement of these pollutants is further influenced by the natural landscape. Hills, valleys, and drainage networks determine the direction of surface runoff, guiding contaminated water through streams and rivers before eventually reaching larger water bodies. A pollution source located several kilometers upstream may therefore affect ecosystems and communities much further downstream. Human activities add another layer of complexity. Roads, stormwater drainage systems, industrial canals, and urban infrastructure modify the natural flow of water, creating multiple pathways through which pollutants can spread. In densely populated areas, contaminants may originate from several different sources before converging within the same river system. Because of these constantly changing conditions, traditional field monitoring has several limitations. Water samples are collected only at specific locations and specific times, providing information about only a small portion of the entire watershed. While these measurements are highly accurate, they cannot fully capture how pollution changes across space and time. To effectively understand these complex environmental processes, scientists require a broader perspective, one that extends beyond individual sampling points and reveals the complete picture of an entire watershed. This is where geospatial technologies become essential, enabling environmental changes to be monitored continuously across both space and time.
One of the most important applications of remote sensing in water pollution studies is the monitoring of harmful algal blooms, commonly known as HABs. These blooms occur when algae grow rapidly due to excessive nutrients, such as nitrogen and phosphorus, entering water bodies from agricultural runoff, wastewater discharge, and urban activities. As algal blooms expand, they reduce water quality, decrease dissolved oxygen levels, and may release toxins that threaten aquatic ecosystems, drinking water supplies, and public health. Detecting these blooms at an early stage is therefore essential for effective environmental management. To monitor this phenomenon, scientists use the Sentinel-3 satellite equipped with the Ocean and Land Color Instrument, or OLCI. This sensor measures subtle changes in water color and detects chlorophyll A concentrations, which serve as a reliable indicator of algal growth. The satellite imagery is then integrated into a geographic information system, where spatial analysis is performed to map the location, extent, and intensity of algal blooms. These maps allow environmental agencies to identify high-risk areas, monitor bloom development over time, and implement timely mitigation strategies before the situation becomes more severe. This application demonstrates how the integration of remote sensing and GIS transforms satellite observations into practical environmental information, supporting faster and more effective decision-making for water quality management.
Sediment pollution occurs when excessive soil particles enter water bodies due to erosion, construction, mining, and agricultural activities. This pollution can reduce water quality and harm aquatic ecosystems. Remote sensing and GIS provide effective tools for monitoring sediment pollution over large areas. Human activities often increase soil erosion. During heavy rainfall, loose soil is carried into rivers and lakes, increasing the concentration of suspended sediments in the water. To monitor sediment pollution over large areas, scientists use Landsat-8, which provides multispectral imagery suitable for assessing water quality. By analyzing the relationship between the red and near-infrared bands, researchers can estimate turbidity and the concentration of suspended sediments within water bodies. The processed satellite imagery is integrated into a geographic information system, where spatial analysis is used to map sediment distribution, identify pollution hotspots, and compare changes over time. The data is imported into ArcGIS Pro for further analysis. The satellite image is displayed as a raster layer, where each pixel contains spectral information captured by the sensor. These pixel values provide important information about the characteristics of the Earth's surface, including water bodies and suspended sediments. The processed raster data is then classified. This classification map allows researchers to visualize the spatial distribution of sediment across the study area and identify regions that may require further investigation. Areas with high sediment concentration can be identified as pollution hotspots. Excessive sediment reduces water clarity, affects aquatic habitats, and may damage sensitive ecosystems. GIS and remote sensing provide a cost-effective and efficient method for monitoring large areas. The information supports environmental agencies in managing watersheds, reducing erosion risks, and protecting water resources. In conclusion, Landsat-8 and GIS technologies play an important role in monitoring sediment pollution and supporting sustainable environmental management.
Thermal pollution occurs when human activities increase the temperature of natural water bodies such as rivers and lakes. This usually happens when heated water from industries, factories, or dams is discharged into nearby rivers. Even small temperature changes can reduce dissolved oxygen levels, disturb aquatic ecosystems, and threaten aquatic species. Because these temperature changes are not always visible, scientists use remote sensing technology to monitor and detect thermal pollution more effectively. Remote sensing and GIS uses satellite imagery to observe and measure environmental changes from space. Landsat satellites equipped with thermal infrared sensors were used to detect water temperature changes. These sensors capture thermal radiation emitted from the Earth's surface and generate thermal maps showing abnormal heat patterns in rivers. GIS, or Geographic Information Systems, helps analyze and visualize the collected data spatially, allowing researchers to identify pollution hotspots and monitor temperature changes over time. One important case study was conducted on the Karun River in Iran, the country's largest river and a major water source for industrial, agricultural, and domestic use. Researchers used Landsat-5 and Landsat-8 satellite images collected between 1999 and 2019 to study long-term water temperature changes and thermal pollution patterns. The study found that dams significantly affected river temperature. During summer, water released downstream from dams was about 3 to 5 degrees Celsius cooler. In winter, the downstream water became slightly warmer. The research also identified pollution zones caused by industrial discharge, urban wastewater, and agricultural runoff. Some polluted areas showed increasing temperatures over the 20-year period. Higher water temperatures reduced dissolved oxygen levels and negatively affected aquatic habitats and ecosystem health. The study also showed that thermal pollution sources had increased over time, especially near urban and industrial areas. Compared to traditional ground-based methods, satellite imagery provides wider coverage, long-term monitoring, and more efficient environmental assessment. This technology helps scientists and authorities detect pollution sources, monitor temperature trends, and support sustainable water resource management. Thermal infrared sensor is an important remote sensing technology used to support various environmental and resource management applications. Ultimately, GIS and remote sensing technologies provide powerful tools for monitoring and managing water pollution through various environmental applications. Sentinel-3 OLCI helps detect harmful algal blooms that can threaten marine ecosystems and human health, while Landsat-8 OLI is useful for mapping sediment pollution and identifying areas affected by poor water quality. Landsat 8 thermal infrared sensor can detect thermal pollution by monitoring temperature changes in water bodies caused by industrial or human activities. Together, these applications demonstrate how GIS supports accurate environmental monitoring, improves decision-making, and contributes to sustainable water resource management for the future.
That concludes our presentation. We hope you found it informative and gained valuable insights from our presentation. Thank you for the attention, and thank you for watching until the end.